Good evening. We should be live now, and I just gave a little pause because it always takes a moment for everybody to drop in, and I didn't want some of you to feel that you had somehow missed the start. Well, first of all, thank you all very much for dialing in on this Thursday evening in order to join me in an evening of absolute delight and pleasure, because with me this evening is Dr. Emma Chapman, and the focus of the evening is going to be her recent publication, Switching on Stars at the Dawn of Time, First Light. So First Light is its name, Switching on Stars at the Dawn of Time. And with me to have a chat and to add some degree of gravitas or understanding of the subject matter is our very own Dr. Greg Brown from the Royal Observatory, Greenwich. Greg, good evening. Emma, good evening.
Good evening.
Good evening.
Well, I mean, I can't, I don't know how I could convey to anybody watching how much excitement there is to be had in reading your book, because it is a great romp full of absurdity. And I just love the fact that it has juxtapositioned so many images in my mind of completely incompatible concepts. And yet somehow it's the first time that I've begun to understand what it is that astrophysicists do and how you might think about things.
Well, that's wonderful to hear. Thank you.
How you came to thinking about it like that, or was it just natural?
I am a very colloquial writer, so I wrote as I thought and then went back with a grammar checker. This is how I love to explain science. So I think I used to get intimidated a lot by I guess the hierarchical structure of academia and think, oh my gosh, people just know way more than me, and it just comes to them naturally. And I just at some point accepted that it was okay to ask questions and it was okay to not understand something. And so every part of my career so far has been about me finding something I don't understand and then going off to study it. And so it's exactly the same with this. With each chapter, I kind of thought, right, what is the question that I want to ask? And then I just went for it. I just went for trying to answer it in every way that made sense to me, which might be a bit of a jumbled place, well, but that's.
I think that's right. You give, but not only do you do that, but you then give permission to the reader and to anybody who's thinking about it to feel the same way. Because one of the things that's always struck me about a celestial observation as a subject is just that people have done it, obviously, from the dawn of time, and they've done it with basically their eyes. I mean, their eyes and their mind. And no matter how sophisticated we get, some of the jumps and the thinking that were first made can't be matched in terms of their grandeur and wonder. So it is something where it is the raw application of the mind to a large extent. So it requires a huge amount of imagination, a huge amount of ability to go a little bit further in your thinking.
Yeah, I agree with that. I think cosmology, which is the study of the history and the large scales of the universe, we can't test that in a laboratory. We can't build a mini universe and poke it. We can't, conjure up a little black hole and figure out what it does. So no disrespect to, physicists that do that and geologists that dig all of this. We really do have to use our imagination. And of course, we can then build telescopes, and of course, we can run simulations. But you have to have an idea of what you want to simulate, what the equations are beneath it, and that requires sorry, I think that was my mail indicator. I'm just going to turn that off. And that requires a huge amount of imagination. Just sitting back behind me, you'll see my thinking chair. So anywhere I've been, I've always had a thinking chair, because sometimes I just need to close my eyes and try not to have an anxiety attack about how small I am and insignificant, and then start to ask questions about how big the universe is. And oh my gosh, like, what shape is our galaxy? Why is our galaxy that shape? And sometimes it's questions that would have been in my A-level physics exam paper, but it's stuff I've forgotten. And it's like watching a film like, I don't know, Inception, like you get it at the time, then 10 minutes later, you're like, oh. It's kind of like that with cosmology with me.
Why had I never understood? But Greg, there's an opening bit in this, which it's in the book, which is just incredible, because it is just like an episode of Doctor Who, because it starts with us on the USS Los Angeles, a dirigible waiting, and on a rooftop somewhere is Edison waiting to see a solar eclipse. And I think that that image of the solar eclipse being watched in 1925, was it? And how people must have felt about it and thought about it. And yet in there, right at the core of it, is some big science.
Well, that actually is one thing I found brilliant about the early part of this book, is that actually that's a story I hadn't heard. I've heard lots and lots of anecdotes in astronomy about all sorts of weird and wonderful experiments that have been done in order to try to understand things, and citizen science as well, actually giving it to the people, to everyone else, to try to get them involved in science, because no matter how many astronomers we throw at a problem, more is always helpful. And this was a brilliant example of the general public being used to get the most accurate measurements of a solar eclipse that we had ever had. And that was an absolutely brilliant story.
Thank you. Yeah, it was one that was new to me when I started writing the book as well, which is why I have loved writing this book, because I learned so much as I was doing it. And for those listening that aren't familiar with this story, what it really sets out is how would I say it? How basic we can go to answer the biggest of questions. And this question was, how fast does an eclipse, how fast does the moon travel, how fast does the shadow of the moon travel across the earth? And so they had these intimidating looking men in trench coats and hats. 3 of them stood like this on the top of each building in Manhattan, and they had them looking down at their feet to see when the shadow crossed them, and somebody else was timing them. And through this, you know, they figured out what the speed of that shadow was, and that it was very fast indeed. And this is just one of so many examples. And as you've said, Greg, citizen science is a big thing these days, which is a fantastic thing, because everybody's got a computer now, so everybody can contribute through that. But it's not new. Citizen science isn't new. We've been using it since well, ever.
Yes.
And that chapter, Over the Rainbow, I mean, it's it focuses, or at least it takes its title, the inspirational point of it, about wavelengths of light and of different types of light. It gets used to some of the building blocks of how you go about observation in a way that will give you information. And so you take us through the electromagnetic spectrum, which I must say, I wish you'd done physics at my school, because then maybe I would have understood something and not ended up doing history and art and law. You know. But it's a really good grounding in just trying to get the fact that not all light or not all electromagnetic radiation can be seen. And of course, you couldn't resist reindeers being able to see the pea of a predator on the snow.
Yeah, this is the kind of segues I really enjoy. Like, this is, I just go down rabbit holes. I didn't know that when I started writing this book. I didn't start to set out a chapter. It was like, I know a really good analogy about reindeers and what they can see with UV light. It's that I was just thinking, like, right, how can I describe this spectrum? I was like, oh, what would it be like if we evolved UV eyes? And then I was like, oh, there are actually animals that can see a UV. Oh.
I think a little bit of information that crossed my mind when I heard that was that the mushroom, the red cap mushroom that has cyclobin in it and is poisonous to human beings, reindeers can eat, but the Inuit drink, or the Sami drink the reindeer's urine and get a trip on the urine, because the process that the poison goes through in the reindeer makes it non-toxic to humans. So I just thought I'd throw that in there because it was reindeers and urine, right?
Yeah, no, please. I like segueing into something completely different. That's really fun.
Now, we probably have a hardcore set of astronomers and astrophysicists online watching us. And I was just, there is a serious point to all of this, which of course is it begins to get you into understanding the nature of light and what it's telling you. Maybe you could just run us through some of that basic thinking of understanding.
Yeah, I keep going on mute, by the way, just because being in lockdown, my babysitter can't babysit, and I have 3 very small children next door, so and 2 hamsters. So excuse any noise that you do hear. Right, the basics of light. Well, the idea of light is that normally we're used to thinking in a very optical sense. So we call light what we're interested in as humans, which is the middle wavelength of all of the light possible. And you have a rainbow, you have a spectra, you have red, orange, Richard of York gave battle in vain, rainbow in the middle. But what's interesting is that over the rainbow in each direction, you've got more wavelengths of light that can exist. So when we go from the red onwards over that way, then you have the infrared, and then you go into your microwaves, your radio, etc. And on the other end, we've got your ultraviolet, your X-rays, your gamma rays, all of these possible wavelengths of light. And everything really in the universe gives off different amounts of light at different wavelengths. And so wavelengths is light can be thought of as a wave, and wavelength is the distance between two of those peaks, with radio waves having a really long wavelength, and for example X-rays having a much smaller wavelength. Now, astrophysical entities like stars, black holes, even planets give out light of well, not planets, but if we're shining a light off a planet, it would it gives off lots of light at all of these different wavelengths. And so that gives us an opportunity to actually see an object in lots of different ways. So this is something that we're really familiar with. So if I break my arm, first of all, you might be able to see, oh, look, that's not the right angle, that's not very good, I better go to A&E. But a doctor doesn't just go, no, that's not great. They actually take an X-ray. They take an X-ray to find out more information about what's been happening. And so we do that with the universe. So for example, you can Google it, but I might even have a picture of it actually here. I'll just do that while I'm talking. So you can observe galaxies which look like normal galaxies that you might be familiar with, let's say spiral shapes and everything. You go, oh, that's a lovely galaxy, it's very large. But when you look in radio wavelengths, what you suddenly see is these fantastic lobes, we call them, so big outbursts of what looks like gas coming out of these galaxies, 2 or 3 times larger than the actual galaxy. And that is the signature of a black hole at the center of the galaxy.
You have a cracking photo of that in your book, don't you?
I'm just trying to desperately find it on my... And so, unfortunately, I don't have it on here.
It's an absolute beauty, that photo.
Yeah, this
is brilliant, because it's actually a topic that I'm particularly interested in, is these supermassive black holes at the center of galaxies. These giant behemoths that are completely hidden in many regards. They're very, very difficult to find in some ways, and yet some of them are actually extraordinarily bright, not because of the black hole itself, but because of lots of stuff falling into the black hole, producing lots of radiation, and then from out of this comes these huge jets and beams of radio light, which we then see for an extremely long period after the black hole stopped producing light of its own. And that's these radio lobes that you get out.
I can actually share a screenshot now if that's okay.
Yeah.
So here, hopefully, can you see this okay?
Yes, it's brilliant. Yes.
So here we've got, this is the middle section from my book, the pretty part. We've got the Centaurus A galaxy here on the left, seen in optical, and then on the right we have it seen both in optical and in radio, and you can see how big these lobes are. So here you look at this and you go, okay, galaxy, and you can't really tell there's a black hole there, but here this is basically like having a sign that says black hole here. Yes. with a big arrow. So it's really, really useful. And I'm just going to share this as well, if you just indulge me. This is what we were talking about a minute ago, where you have a whole spectrum of light along on the horizontal here. And this is just the rainbow part. This is just the optical part that we're used to seeing in. And this is actually one of my favorite plots, as simple as it looks like, because on the yellow line here, you can see what distribution of light the sun actually gives out. And so this is the bit we're used to, but actually there's all of this as well, and you can see that it actually peaks in the green. So the sun is actually mostly green rather than anything else.
Now I'm gonna have to stop you there, because I mean, people can say, look, I've seen the sun, it's yellow. It can be red on exceptional circumstances. It is not green. And this is one of those, now, dare I say it, is this really a thought experiment where you say it's green?
Yeah, this is. I was careful in my wording when I said that it was mostly green. So as in, it peaks in the green, but actually what the light is doing, what the sun is doing, is it is emitting at all different wavelengths. And as you will know from your GCSE physics, when you mix all of the colours, you get white. You get white light. So yes, the sun is, you know, all of these different colours, but then when the radiation goes through our atmosphere, all of the blue, all of the shorter wavelengths, like your blues, your purples, they get scattered all across the sky. That's why the sky is blue. And so you're left with those longer wavelengths, your red, your oranges, your yellows. So that's why the sun looks a lot more yellow than it would when it started to be actually emitted from the sun. And that's also why you get red sunsets, right? Because the sun is much further down. There's way more atmosphere for the light to get to. There's way more scattering. Even the orange and yellow are scattered off at that point. You're left with a beautiful sunset.
Well, one of those funny facts that somebody told me at the observatory, and I think it was probably your colleague Emily, was that on Mars, the sky looks red,
yeah,
but when the sun sets, it goes blue.
Yes, this is oh, you put me on the spot here. Let me try and remember what's causing this. So this is due to scattering by different particles in the atmosphere. So in our atmosphere, it's mostly scattered by the gas particles in our atmosphere. In Mars's atmosphere, if I remember correctly, dust plays a much bigger role, and the larger particles scatter light in a very different way. So you end up with blue being the sunset and red being the daytime. Perhaps Emma can correct me on that if she happens to know, but I believe that is the way that it works.
Yeah, I don't do planets.
No, okay. So yes, at the very least, we do have this weird flipping of how things work in the atmospheres on different planets. So yeah, the sun appears yellow to us on the Earth, but on Mars it might appear a different color. On a different planet it might seem different. And also there's an element of the structure of our eyes being important as well. So we have, our eyes are built to collect red, green and blue light in various different levels, and the combination of that produces white. If our eyes were structured differently, we might see the sun very differently indeed. If we had eyes capable of seeing it in ultraviolet, for example, then we would see something very different indeed.
Yes. Yeah, no, it is absolutely mind-blowing, and the light tells us a lot about the physics, but it also, we have a built-in emotional reaction to it, to color, don't we? And that just touches on somebody who your book mentions quite a lot, as somebody that you know and of whose work you've admired, Emma, which is Katie Patterson, who's the artist in residence at Royal Museums Greenwich for last year coming round now to the end. and she manages to combine an artistic interpretation as well as a scientific comprehension of the nature of light in the night sky.
Yeah, so Katie was the artist in residence when I was a PhD student at my former university, and I remember her for just her quiet intensity. she just sat at the back and was absolutely rapt to whatever seminar was going on. She was just noting it all down furiously. And it was only years later, actually, when I was researching for this book, that I found this wonderful image, which I'm going to share with you in a moment, of the average colour of the universe as it changes. And I thought, oh gosh, that's really useful. Who's it by? It was Katie Patterson. So it was a really wonderful thing. So is now a good time for me to just quickly share that?
It's quite an important concept here, isn't it? I mean, I know that this is an artwork, but it is also a really important concept.
Yeah. So what Katie did here was, with an astronomer from UCL, what they did was they figured out the average colour of the universe at all times that the universe has existed. So annoyingly, they couldn't get me a photo where this was at 12 o'clock where you'd want it to be. But here is the beginning of the universe, which is sorry, I've just been put on the spot. Yeah. here when it goes white blue. So you've got the universe, which is really white hot with all of the goings on. So you've got, you know, very, very hot hydrogen, very, very hot helium, photons zipping around everywhere. And then it starts to cool down into the yellower and the red, so it's starting to cool down. And then it goes dark altogether. And this is what we call the dark ages of the universe, because there was just nothing much happening optically. And then here, when you get a sudden bright blue flash, that's when the first stars came alive. So they suddenly changed the universe. They lit up one by one all of the universe, blue, white, hot. But very quickly, well, not very quickly really, but they are replaced over time to, we're about here now. We are, what our average colour now is what's called cosmic latte, I think it was,
Yes,
which
that's right.
was just some PR officer's joke, I think, because it's just beige. Just let it be beige.
So, so Emma, does that mean that it's not a bar Easter but a star Easter?
Yeah, very good. How long have you been thinking about that? Oh my goodness. Yeah, this is amazing artwork, and the reason it's not at 12 o'clock like, I don't know, my intuition wants it to be, is because it spins. So when you actually see the artwork in real life, it's a spinning disc, and this is a beautiful picture by a photographer. Yeah, and it spins, so they just didn't happen to catch it.
So really, I mean, the important idea encapsulated there is that there is transition, and that transition is in different phases, because that first period is not the same necessarily as the changing of colours in the second period. There's something more fundamental going on, because what happens, how does the Dark Age arise? Okay, so this is the Dark Ages here. And what we're seeing here is all of the light in our universe cooling down. The universe is expanding, it's cooling down, and as it cools down, these photons lose energy. They're fighting against the expansion of the universe. Everything's cooling down, and so they go through the infrared wavelengths and into the kind of stuff that we can't see, like the microwaves and the radio, this kind of thing. So optically, we can't see anything. So if you were Doctor Who and you took your TARDIS off to this time, you'd open your doors and you'd see black. But that doesn't mean that nothing's happening. So I'm just going to stick with this the whole night. It's perfect. So on the background, what's happening on the left here is you've got what is called a web of dark matter. So if you had eyes that could see dark matter somehow, then this is what you would see in the Dark Ages everywhere. And as the Dark Ages, this lasts, let's say, 180-ish million years, this Dark Ages. And then suddenly what happens is the hydrogen that's in the universe is depicted on the right here. Is the two overlaying images, both are happening at the same time. It's just that they've separated them to show you how easily how much the hydrogen follows the web of the dark matter. It's pulled in gravitationally. All this hydrogen falls in, it gets compressed really, really close together with gravity, and boom, you get your fusion. And so it's only with this that you get those first stars starting and ending the Dark Ages here with this blue flash. And they live very quickly and they die very quickly. When I read your section on this, particularly on the web, it made me, you know, what that came to my mind was just the idea of the way that water, or, you know, in those autumn days, you get mist condensing onto a spider's web, and like you get water droplets forming on a spider's web, and I was just wondering, I mean, is that it's the temperature, it's somehow that dark matter structure causes some sort of increase, or it's gravitational pull, isn't it? It's gravity. Mm-hmm. Yeah, it's gravity. It's not a temperature differential in that sense so much as a pulling together of matter.
No, but in similar ways to how that dew that's caught on your spider's web will potentially follow those webs and actually join up in the places where the joins between those webs occur. Exactly that sort of thing is happening in these filaments. The material is being sucked effectively down these filaments and joining together in these big bulges where the web comes together, and that's why you end up with these huge collections of stuff, where you get large clusters of galaxies all forming in the same place, and then huge voids where all the stuff has been pulled away to the web. So yeah, the analogy is it's partially accurate. Yeah, absolutely.
If we go back to our process of our sort of images of people in coats and in dirigibles and standing on roofs, we go into quite an exciting period of science. But I wanted to talk a little bit about Celia Payne-Gaposchkin, who you mentioned in the book. And she's the first person who really begins to think about what it is that they've been chasing, because they've been looking for some sort of special sun material, have they? That they think the sun's made of sort of sun matter or something. And she has a brainwave. Yeah.
So when they were standing on top of the rooftops in, I've forgotten now what year that was, but in the 1920s, they were on this rooftop, and there was this one man who stood on top of a dirigible, massive airship, with a video camera in the 1920s, cranking it, taking these wonderful images, because they were looking for something called coronium. And coronium was the theoretical element that they thought the corona, which is the outer atmosphere of the sun, which I'm just going to share again while I talk about this. Okay, so here we've got the corona, really nice coronavirus. Let's just make that link now and get it out the way. Yep, there it is. So corona can only be really revealed when the main sun is hidden, because it's very, very faint, but it's also very, very hot. So it's millions of Kelvin compared to the, say, 6,000 Kelvin that the surface of the sun is. That's weird. Why would it get hotter the further away you are from the star? And they thought, okay, we've seen this element here, but what it actually ended up being was iron. It ended up being iron in a very highly ionized state. Now, in 1920s, most people thought that because the sun had things like iron and carbon and all of these things that they could measure looking at the light, they thought it must just be a hot Earth. So the sun, if you heated the Earth enough, it would radiate like the sun. That's the difference. End of story. Celia Payne-Gaposchkin, here in figure A, is doing her PhD thesis in Harvard, 1925, and she produces a thesis which says that you're all wrong, that actually the stars consist of a huge amount of hydrogen, a huge amount of, well, a little bit more helium, and then not really any other elements at all. So I'm going to call them metals. As astronomers, we round up the periodic table to hydrogen, helium, and metals because it's just easier. And so she said that no, the metals are actually very, very small. Yes, they're the same as what we find in Earth, but the ratio to the hydrogen helium is much larger in terms of the ratio. Yeah, people didn't believe her.
And they had good reason not to believe her, didn't they? Because I suppose they would have said, well, look, how can that be? Because we know that the Earth is under the gravitational pull of the sun, so the sun must be massive. And if the sun's made up of helium, which isn't very dense, then, or hydrogen, it doesn't really work, does it?
It's counterintuitive. And I think a lot of these discoveries, you get yourself into a position where all of the theory points to the fact that stars are hot Earths. Having someone go against that,
yeah,
you know, even today we've had, maybe we'll touch on it later, but we've the first detection of this time is very counterintuitive. Sorry, the first detection of the first stars that we've had in has revealed things that we just never expected. And it's taking, you know, years of my community going, no, that can't be right. That can't be right. And I'd just love to see us in 5 years at how normal it is at that point. But yes, Celia Payne-Gaposchkin, she did a huge amount, but people didn't believe her at the time. But it was only a couple of years actually before people found a lot of evidence supporting her. It did get accepted in the end.
Brilliant. So we get an understanding, a greater understanding of our sun. We begin to see other galaxies, and we start to understand something of the universe. And then we have to make way for bird poo, because we start to understand something about the time in this scale, in terms of there having been a beginning. And I know that, of course, there must have been, if there was a lot of argument about Darwin and monkeys, there must have been a huge amount of resistance to the idea of the beginning, and the beginning being something tangible rather than the word, rather than Genesis actually being something really tangible. And yet, there we are in 1950s, and it's discussed, and something points to clearly to the Big Bang. Do you mind just shaping us through that, because it's going to lead us on eventually to talking about the center of your book, which is that first generation of stars.
Yep, I'm going to share my screen again and make everyone feel a little bit sick with the dizziness of it. Yeah, so picture this. Here we have two fellows, Holmdel and Penzias and Wilson, with their Holmdel antenna. It's an ice cream cornet kind of shape. That's what they say. I've never quite bought that, but it's sideways. And the idea is that all the radio waves on the sky get funneled in. I'm just using my hands there and realise you can't actually see them. Funneled into here, and they get focused into the observatory box, and that way you can see the radio waves on the sky. So what these two guys did was they walked up to the telescope with a rough idea of what they wanted to do. They wanted to kind of measure the temperature of the galaxy around them, for whatever reason that's got lost in history. And they turned on the telescope, and it had been left at a different frequency by the previous users, and they heard a fizzling, I guess, in terms of what they would see on the data. And if you can imagine the static on your television, it was if you remember antenna television, they used to be static, kids, and you used to be able to hear this. And that was the kind of noise they heard, and so they pointed the telescope in every direction, going, "Oh, we can't do our measurements if there's this noise. It's not a correct scientific observation." They pointed it towards New York. It was still the same. Pointed it straight up in winter, in summer, in spring, still there. So you can imagine how annoyed these guys are getting. And then they find that there's some pigeons roosting just about here, right by the observatory box, really nice and warm. And they decide it must be the pigeons' fault, so they clean the pigeons out. And shall I go right into that story? Do we have time?
Bang bang. Okay.
Yeah. Okay. Let's cut it short. They shoot the pigeons, clean out the telescope, and find that noise is still there. And what I say, of course, but what they were measuring was what we can see just below that picture, which is the cosmic microwave background. So this is the radiation left over from the Big Bang. Imagine you're next to a horrible explosion. You shield your eyes. You go, "Oh, the light." You see this all the time. I've got sellotape, sorry, fiddly. And you see people go, "Oh, the light," and it's because big explosions, lots of radiation. The Big Bang, pretty much the biggest explosion that you can think of, and so the radiation that it produced is still around today. It's a very hard thing to think about, but it's pervading the whole of the universe all the time. And so as that expands, it's still everywhere. It's just that it's a lower energy. And so now it's still there, but it's in the microwaves, it's in the radio, so you can pick it up. And that's what we measured in the 1950s, and then moving on in 1960s, and then moving on. We've got better and better and better at measuring this. And so now is it irrefutable? Dare you ever say that? But it is irrefutable that a Big Bang happened in science, and that was one of the key areas.
If you don't mind, Emma, I've got to sort of just dive in to speak up on behalf of just the madness of it all, because if you're from my kind of background, I mean, I was brought up in a religious household, and I was brought up probably with a very classical view of the universe. If we ever talked about it at home, and we didn't often, it would have been somehow that it was an infinite amount of space in some kind of Euclidean structure, like an empty wardrobe, where nothing was connected other than emptiness, and then there were sort of planets and stars hanging around in it. So the idea that you would get stuff bouncing back or hanging around or an afterglow from an explosion is completely counterintuitive to that kind of fundamental concept of what a universe might be.
It is counterintuitive. Funnily enough, at lunchtime today, I was on a Northern Irish religious programme talking about this, and they said, how can you reconcile this with faith? And I did explain that I'm not of the faith. I'm in the purely in the scientific camp. But I said that every theory, I think, whichever theory you subscribe to, has some madness in it, has something that is very difficult to grasp. So whether that's Big Bang Theory, which absolutely everything coming from nothing. How is that? And I always say that's a place that faith can come in. Actually, I know that's some of my colleagues that do have faith. That's where they say, well, what triggered the Big Bang? Maybe it was a divine presence. That's what we were talking about at lunchtime today, actually. But if you think of this purely on a scientific stage, then when the Big Bang was being questioned in the 1940s, 50s, then there were people saying exactly what you've just said. We live in an infinite universe. It's infinite in time. It's infinite in space. It's always existed. But then that has its own madness in that we know it's expanding. So where's all the extra matter coming from? And the Big Bang Theory, it's important to me, obviously, because if you don't have a first of everything, if you have a steady state universe, as we call it, where nothing changes, then there wasn't a first of anything. And so my entire career is pointless. Really, I like the Big Bang Theory. That's where my money is.
You wouldn't be the first person to have felt that about their career. That's absolutely great. Take us to the archaeology, because another really lovely, strong image is of your Lord Carnarvon and Carter and the Tutankhamun expedition, because you're an archaeologist of space, trying to look in and raid tombs of information. So talk us through it.
Yeah, let me just see if I can just share this for a moment. So when I was a kid, I wanted to be an Egyptologist. It was the coolest thing that I could possibly think of doing. Firstly, it's all very difficult, this Zoom stuff, isn't it? There we go. So this is what I wanted to do when I was a kid. And on the left here, you can see Lord Carnarvon and Howard Carter chipping their way into Tutankhamun's tomb. And as they opened it, he famously said, I'm paraphrasing here, "What can you see? Wonderful things everywhere, the glint of gold." It's a really fascinating time to look at. Now, I ended up doing different things. I ended up going into something of a bit more of a cosmic nature, looking at opening the tombs on a much larger scale. When we look at the first stars, we're missing about 1 billion years from the timeline of our universe, which is a huge chunk to miss. And I feel sometimes that the career that I do now is very much about opening the tomb on that 1 billion years.
It's
slide.
It's an awe-inspiring idea. I mean, Greg, did you ever think about the past when you were thinking about the sky?
Well, it's impossible not to in many ways, because of the nature of astronomy. When you are looking at objects which are extremely long distance away, because light doesn't travel instantaneously, you are always looking backwards in time. So actually, in fact, nothing that we ever experience is in the present. It's always slightly further back in time. Now, when we're talking about things on the scale of a room or a city or something along those lines, they're so close to instantaneous as it makes no difference. But when we're talking about looking at our next nearest star, that's 4 light years away. So that's looking 4 years backwards into the past. When you're looking at the nearest galaxy, that's 2.5 million light years away. So that's 2.5 million light years into the past. So astronomy is inherently archaeology, because everything that you're looking at, with the exception of things in the very, very, very close parts of the universe, is stuff that's a long way away. And in fact, Emma's brought something up to show this.
Yeah, so here is, I couldn't resist because I spent ages on these animations. You wouldn't believe how long this took, so I had to hijack what you were saying. So this is you saying hi to a friend on Mars, and your friend's waving back, and you've actually got quite sad after 8 minutes because you think they've ignored you. And as Greg said, we see the sun 8 minutes in the past, so we wave to our friend on the sun who happens to be able to withhold those temperatures. Goes back 8 minutes later, oh dear, now we're very sad because our friends completely ignored us, and it's 16 minutes. Nearest galaxy, 2.5 million years. I love how we're basically prepped off the same speech, Greg. 2.5 million years. We all just get given a sheet as astrophysicists.
Yeah, absolutely, yeah.
And of course, by the time that the lights return to you from your friend, then you're very much dead. So there's no point. And that's why I really enjoy thinking about what an alien on Andromeda would actually be seeing. They wouldn't be seeing us. They'd be seeing one of the earliest ancestral branches of humans evolving, which is the Homo habilis here, 2.5 million years ago. So we'd have to wait another 2.5 million years for them to even see, you know, Gogglebox or whatever it is, and all of the wonders of Earth. Let me just see if I can. So now we go back onto the annoying thing is my mouse is disappeared on this.
Yeah, amongst all the sellotape that you've got on the desk, admit it.
So you should see my desk. It's terrible. It's for a cool reason though. I was just packaging up loads of. Yeah, I was just packaging up loads of editions of my book to go out to my relatives.
Ah, very nice.
Sellotape everywhere. Right, back to archaeology.
And
there's lots. Oh, sorry.
No, I was just going to say, because you we've talked about dark matter, but we haven't. But there's a reason for why. I mean, I'm not sure who or what period people really began to take it seriously or begin to understand it. But again, it's one of those things that obviously we can't see it, but that doesn't mean it's not there, because it is apprehendable. It is apparent in its impact. So even if you're not sure what it is, you know it has to be there. In fact, you use that Sherlock Holmes quote about when you've excluded the possible, the only thing left, no matter how improbable, must surely be the truth, or something like that. Or you've probably got this. I haven't. I've confused it.
No, that's right. So if you're talking about dark matter in general, again, it's one of these concepts that everyone has fought very hard to make it not true. But against our best wishes, it still does seem to be true. And it's only through a lot of people making incremental roadways into this impossible idea that the universe is actually mostly made of dark matter, or the matter in the universe is mostly made of dark matter. So, you know, it's 25% compared to our 4-ish of dark matter. We only know it's there because of how galaxies rotate, and we see that actually galaxies are rotating so fast, the stars are moving so fast in these galaxies, that there has to be something really huge throughout this galaxy, and the luminous mass doesn't match up. So there has to be something dark, hence dark matter. So we know it's there, but dark matter is famously very difficult to interact with. The only way we can see it is gravitationally. So through it's how it pulls in matter. So for the hydrogen, for the first stars, for example, how it makes stars go quicker around in a galaxy. But can we find the blooming stuff and trap it in a test tube? No.
And along the way for understanding, because one of the things we ought to touch on, I suppose, because it's one of those core principles as well, is redshift, blue shift. I do like the fact we have all these colors, redshift, blue shift, and black holes and dark matter. But the redshift, blue shift gives you what exactly? It gives you movement?
Yep.
Or direction or acceleration, I suppose.
Yep, sorry, I was just getting to a slide that I want to show on this. Yep, okay, so can you see the PowerPoint?
Yes, yes.
Good. Okay. So if we move that, can you see that nice little animation?
Yes, we can, yes.
Good. Okay, so what we have here is in the middle, we have what we might see static. So we're looking at the light coming from a different galaxy, let's say just a galaxy nearby that happens to not be moving towards or away from us in the middle. And what we can see here is what we call absorption lines in the spectra. So if a galaxy has lots of calcium in it, for example, so that's a metal, lots of calcium, then the photons that are most favoured to be absorbed by calcium, they'd all get guzzled up by the calcium, and so we'd see an absence of them. We'd see a dark line in the spectra. Now, what happens with redshifting is that if a galaxy is moving away from us on the top, then how we perceive where those same calcium lines are gets shifted up to the red end of the spectrum. It's redshifted. On the bottom one, as you see it moving towards us, then those calcium lines are blue shifted. And so we can turn this around. And if we start measuring galaxies with lots of redshifting, so we know where calcium should be, because unlike dark matter, we can trap calcium in a test tube and we can shine light at it and see which absorption lines it creates. So we look and we see and we go, oh my goodness me, that's very far away in terms of redshifting. It must be moving away. And we can also define like how fast it's moving away as well. And what we see around us is every single galaxy, basically apart from Andromeda, moving away from us very, very fast, which was another piece of evidence for the Big Bang.
Yeah, fantastic.
So,
now, I'm going to have to interrupt our train of thought, only because a couple of our participants have asked, of our listeners have asked for questions, and I thought I'd just pop them in, and then we'll come to you afterwards, Greg. But have the panelists read? I'm going to read all three of them, and then we can just have a crack at them, or you can have a crack at them. Have the panelists read Pullman's Dark Materials? And if they have, what do they think of the science in them? That's one. What in percentage terms do you think we know about the universe? And the last one was, what unexplained phenomena would you like to find the answer to? I think you'd like to find the first star, wouldn't you? You put words in your mouth, Emma. I'm notorious for telling people what they think because it's what I want them to think.
Yeah. Right, Pullman's Dark Materials. I don't mind leading with that, Greg, if you're okay, and then you can chip in.
By all means, go for it.
My first daughter is called Lyra, after Lyra from Philip Pullman's Dark Materials. So excellent link there to whoever asked that. I haven't read it for a very long time now. I did read the graphic novel again recently. I think what Philip Pullman manages to do really well is take something which he calls dust. So dust is pervading. It's almost like this magical thing that connects people, this dust. And I think he takes, what he does really well is he takes something that isn't known and how it can be perceived as magical. But once you start understanding something, it goes from magical to science. And I think that's what I actually drive home for my daughters, is when I got in trouble in the playground because I told them that unicorns weren't real. And all of the friends found out and they were crying, and the mother, anyway. And I told them that magic doesn't exist, but science does. And that actually magic, as we see it, is just something that we haven't explained yet with science. So I'm taking a bit of a segue there, but yeah, I couldn't go into minute detail about the science that he uses in the book, but you can tell that he is thinking like a scientist.
And thinking about that interaction maybe that we talked about at the start about how you feel about origin stories or belief. I mean, I can't imagine for a moment that WIMPs are going to turn out to be dust. So another great line from another great expression from the world of astrophysics. So WIMPs is weak something particles.
Yeah. Greg, do you want to go into this one?
He looks like he's having a good laugh. I don't think that was an insult, Greg. It was just
weakly interacting massive particles, yes. So there were what dark matter might be, and it was a fight between machos and WIMPs, and I can never remember what machos actually stands for, but it's stuff that's normal but just for some reason we can't see. So it's planets and dust as in normal dust rather than dust as in this magic Philip Pullman dust, gas and rocks and black holes and all sorts of things that we already knew existed, but that were for some reason difficult to see. But no matter how many times we tried to pile everything in macho's favor, it could never come anywhere near what dark matter, the amount of dark matter there was in the universe. It just couldn't come even close. So the alternative was weakly interacting massive particles. These are things that we do not know very much about because they are weakly interacting. They don't interact with us in almost any way except for gravity. So they have mass, so they are massive particles, so they have gravity, so they can pull on things, but they don't, if they come close to you, they pass straight through you. They don't interact with light, so they don't reflect it, they don't refract it, they don't diffract it, they don't do anything really with it except what gravity can do. And we're hoping weakly means not entirely no interaction whatsoever, because we're hoping that one day we'll be able to see some sort of weak interaction between this stuff and the rest of the universe that isn't gravity, and finally be able to prove that these WIMPs do actually exist. But yeah, acronyms and indeed backronyms are the bread and butter of astronomers. Trying to find clever ways to say what we do with random letters it's half our job, frankly. Yeah.
Did you see that latest one where they've actually created a telescope project called Acronym with ACRONI?
It's so in the cosmological disco, it's WIMPs versus machos.
It is WIMPs versus machos, indeed. Although it appears the WIMPs are going to win.
Yeah, the WIMPs are winning, which is stereotypical what a physicist would want to happen, right?
That, yeah. Any of this is true. It's so full of the wish fulfillment of physicists. Now we've got a few questions to tiptoe through because unfortunately we're beginning to run out of time. And I just wanted to. What percentage of the universe have we understood, or how much of is there still to discover, was one question. And I'm going for 17.5%.
Yeah, I was going to go for like 18. So yeah.
It's not bad. Not bad. Yeah.
This is a difficult question, right? And I actually think that it's a fractal question in that we can understand, let's say, exoplanets 1%, and then suddenly we find our new exoplanet and we're like, oh yeah, we know it 100%. Oh wait a minute, I don't understand about the cloud cover on exoplanets, which is what a colleague of mine does. They tell the weather on exoplanets. And so we always find the next thing. And so it might seem like we're narrowing, but we're finding out the same kind of information. And so right now in my field, we know 0.5%, 1% of what's going on in this missing billion years right at the start of the universe. How did the first stars grow? When did they grow? Did they grow in families? Were they completely on their own in the sky like fireflies in the night? How did black holes grow so large? You have to go back to the baby steps of the universe, because what we're missing is, if you imagine a child's lifetime, or human's lifetime rather, we are missing everything in our scrapbook from the day they're born to their first day at school. That's the equivalent scaling of what we're missing in terms of the knowledge of our universe's timeline. That's huge. That's a lot. So that actually leads into the second question that you were saying as well, is that is my unexplained phenomena that I would like to know. I want to fill in those billion years and find out how those black holes grew so large.
Now, two more questions sneaked in along the way, and one was when did black holes form, and the other one was are there any experiments going on now around dark matter?
Yep. Okay. Black holes formed at midday, and they so on the 27th of June.
Which day? 1901.
There we go. When black holes formed, I feel like I'm saying this again and again, but I don't know. We've got an idea. So we think that black holes form, let's say, oh, put me on the spot here, 400, 500 million years after the Big Bang, let's say, around that ballpark. So the universe is 14 billion years old. So black holes formed quite early in the scheme of things. There is one really interesting subtlety here that I'll just touch on, which is the idea that the first stars were so massive, sometimes up to 1,000 times the mass of our sun, possibly, that they could have, the cloud could have collapsed, and whereas normally you get a protostar, there's so much mass that it carried on, and it ended up being what we call a direct collapse black hole. So a black hole that doesn't come from the explosion of a star like every other black hole we know, but it's actually straight through the stellar stage, straight into a black hole. And if these direct collapse black holes exist, that would be more 150, 180 million years after the Big Bang, touch earlier. But the key is it would have given them time to grow into the supermassive black holes that we see today. And it's one of the only explanations that we have for that. So that's, yeah, that's the answer to that one. And as for dark matter experiments, Greg, can you speak more on that one? Do you?
I mean, well, there are dark matter experiments going on all the time, whether they be astronomical or particle physics. So there are experiments. I'm not going to be able to remember the names of any of them, I'm afraid, even though they do have fantastic acronyms. But they're buried deep underneath the ground to try to hide it from all of the cosmic rays and all the nonsense that's going on in the rest of space. And the only thing, hopefully, the only thing that will be able to get through are dark matter particles that will be able to come into the experiment and trigger something. And those experiments have been running on and off for a decade or more, and to particles to date. So that's great. And as to astronomical dark matter experiments, yes, all the time we're trying to find new evidence to show that they exist, that could self-annihilate and produce X-ray light from certain places, but it's expected to be so very, very faint that actually detecting it is going to be a really, really big challenge. But that's not going to stop astronomers from trying, at least sometime in the future.
And well, you know, I think it's been an absolute delight to talk to you both this evening. I don't know if there was anything that you wanted to pass on, any Christmas message before we wind up. Emma, is there anything that you wanted to pass on to our watchers this evening, or our listeners?
I could leave you with a quote. Not for me though. This is my favourite quote around this area. It's what I start my book with. I love my book, please buy my book, but what I want you to take away from this is the feeling of my book, which is that we are pioneers in terms of space. We are very young in terms of finding out what's going on around us, and these first stars, they seem to be the most wonderful things. And even going back to when Ralph Waldo Emerson said all of this, we still have the same feeling about these first stars. They were alive to us, and I like to tell their stories. Thank you.
And Greg, is there anything you want to leave us with?
I'm not going to be able to beat that, so go. Yeah, that's absolutely fine.
Well, I'm afraid I've got something to add, which I can only commend to you. Emma Chapman's book. It's absolutely wonderful. It's a real delight. I mean, it's whimsical, it's funny, it's entertaining, it's informative, it's seriously questioning, and it leaves you in a state of rapture. And I've really, really enjoyed reading it. It's called First Light, Switching on Stars at the Dawn of Time. And so I would really recommend that if you have any stargazers in the family, this is what they want for Christmas, even if they don't know it yet. And there's a link that you can pick up on the chat here that will give you an opportunity to go straight to that book and no doubt to buy it. I just have to leave you with one request on our behalf, which is, as we come to the year end, if you've enjoyed this evening, I hope that you'll think of us at some stage and come and visit us. We'll be opening on the 2nd. And even if you might like to leave a donation, and we'll give you a link for that as well, because you know, every little will help in these difficult days. So there's a link there you can pick up as well. So it just rests with me to say, as usual, thank you very much to Dr. Greg Brown, who is one of the stalwarts at ROG and one of our public astronomers, and also a very heartfelt thank you. So nice to have met you and to have enjoyed this evening with you, and I wish you a very Merry Christmas. Dr. Emma Chapman, you're a star. Thank you.
Thank you very much. That's very kind.